Hello and welcome back to Multivariable Calculus. This is a video course that extends my real analysis course to higher dimensions. And in today's part 2, we will generalize the continuity in this sense. However, before we start, I really want to thank all the nice people who support this channel on Steady via PayPal or by other means. Now, as I already told you, the topic for today is about continuous functions, and you might recall this is a very important property. In a rough sense, for functions from R to R, it means that the graph of the function does not have jumps. More precisely, as you might recall, we can describe this property with the epsilon-delta criterion. There, we would fix an error epsilon on the y-axis, and then, corresponding to this, we will find an error delta on the x-axis. Now, if this holds no matter which epsilon we choose here, we call the function f continuous at this point here. Indeed, this is what you might know as the epsilon-delta definition for continuity. Moreover, you see, it immediately tells us for a continuous function, small deviations in the input result in small deviations in the output. And there you should see, to say that such an error here is small, we need to measure it on the x-axis and on the y-axis. Of course, this is important here and no problem for us in R because we have the absolute value. However, before we do this, you should recall that we can describe continuous functions from R to R also with sequences instead of the epsilon-delta definition. There, you just need to take any sequence xk on the x-axis that converges to the point x. Of course, this point x is what we find here. It's the point we talk about. It's the point where f should be continuous at. And in fact, it is continuous there if for any such sequences here we have that the sequence f of xk is also convergent, namely to f of x. So you see, this is the same idea. If we get closer and closer here on the x-axis to this point x, we should also get closer and closer here on the y-axis to the point f of x. Okay, but there please note, here for this convergence we need to measure the distance on the x-axis, and for this convergence we need to measure a distance on the y-axis. In other words, in both definitions we need to measure distances. Therefore, this is the first thing I want to talk about today. Indeed, one can do this in a very general, very abstract context, but I will concentrate here on the Euclidean distance. So if you are interested how to do this in so-called metric spaces, my functional analysis course can help you there. However, for functions with domain Rn and codomain Rm, I think it's helpful to first start with the so-called Euclidean metric. In other words, the question is now, how do we measure distances in these higher dimensional spaces? Of course, there are a lot of different possibilities, but the Euclidean distance is what you can see as the natural choice. Simply because this is what you will do in the plane in the space R2 when someone asks you what's the distance between 2 points. There you would go with the straight line and use the Pythagorean theorem. In other words, you have something in the x direction and in the y direction, and then you combine both things in the Pythagorean theorem. And then, of course, without a problem, we can immediately generalize this to n dimensions. So we just take 2 points, 2 vectors from Rn, and let's call them x and x tilde. And then we know each of these 2 points has exactly n components. And this one here we just call x1, x2 and so on. And similarly for x tilde we have x1 tilde, x2 tilde and so on. And then we define a new map we call D, where we put Euclid in the index. And of course, this here should represent the Euclidean distance between the point x and x tilde. Therefore, we already know this should be given by a long square root, where we have squares added inside. So first we have the difference of the first component squared plus the distance of the second component squared. Okay, and here you know the square root of these two things in R2 will give us the length of the hypotenuse. Therefore, the only thing that remains now is to generalize this fact to n dimensions. Which simply means we continue with the squares here until we reach the last components. Okay, there you have it. This is the definition of the Euclidean distance, which works in Rn and of course also in Rm with m components. In other words, with this new object, now we are able to generalize the concepts from one dimension. For example, if we can measure distances, the convergence of sequences in these spaces makes sense. Hence, I would say, let's now define the convergence for sequences in Rn. And there you will see this will look exactly the same as in our real analysis course. However, one crucial difference here in the notation is that for sequences I will use an upper index. Simply because the lower index here is already used for denoting the components of the vector. Sometimes this can be confusing and therefore I just take this upper index here for the sequences. Therefore here please don't forget, each member of the sequence xk is a vector in Rn. Most importantly, the dimension here is fixed. All vectors involved here have the same number of components. Moreover, also the potential limit point x is a vector in Rn. Okay, and now we say that the sequence is convergent to this point x in the space if for all epsilon greater than 0 we find an index capital K such that for all indices afterwards the distance between the point x and xk is less than epsilon. And of course, the distance function we use here is the Euclidean distance from above. So you should see this is exactly the same definition as for one dimension, but now instead of the absolute value we use the Euclidean metric. Moreover, you should see if we choose n is equal to 1 here, we get back our absolute value. Therefore, this here is indeed a generalization of our concept of convergence as we have learned it in the real analysis course. And exactly for this reason, we are able to use the same notations. For example, if we have convergence, we can use the limit symbol. More precisely, the limit of xk, where k goes to infinity, is equal to x. Or even shorter, we can write xk goes to x. And in the case there is a danger of confusion, we put k to infinity on the arrow. Okay, so in summary, you see this is a new concept for the space Rn. Now it makes sense to talk about convergent sequences in the space. However, already before this, it was possible to talk about convergent components of the vectors. In other words, we immediately find a connection between the old definition and this new one. More concretely, this new definition now tells us that we can write limit of a vector. So if the sequence xk is convergent, this vector goes to another vector. And now if we write it like this, the convergence is meant in the sense of the new definition from above. So the objects that converge are the vectors as a whole. In other words, writing the vector with components does not change anything. However, on the other hand, if we write limit k to infinity of x2k is equal to x2, then this is exactly our old definition because it's one-dimensional, it works in R. And now of course we could write this thing for all other components as well. More precisely, we would say we have it for xj, where j goes from 1 to n. Okay, so in summary, you see here on the left hand side we have the new definition of convergence, and on the right hand side we have the old one but n times. And now the good thing I can tell you, both things are connected equivalently. In other words, the new definition here of the convergence can be described by using the old definition for all the components. And maybe just consider components might be easier for you. However, this equivalence here is not completely trivial. One really needs to prove something here. So this is not what we do in this video here, but I think it's very important that you already know this fact here for Rn. Indeed, it can help you in a lot of examples. However, before we talk about examples, let's close the topic here by defining the concept of continuity. So let's consider again a function f from Rn to Rm and also a point x in the domain Rn. So this is the fixed vector x where we talk about continuity at this point. So again, continuity is a pointwise property. Okay, now for the definition, I would say let's go with the sequence definition. Here the idea is the same as before. We consider all possible sequences xk, and if they converge to the point x, then the conclusion should be that the images also converge. More precisely, here we now have a sequence on the right hand side, so in Rm, and this sequence should converge to the vector f of x. Okay, now please recall, in real analysis, in our one-dimensional case, we had essentially two cases. The one where the sequence comes from the left side and one where the sequence comes from the right side. Here, please note, this is no longer the case. We have a lot of different directions here. Even if the domain is just R2, you see we have infinitely many possible directions. Even more, a sequence could converge in a very strange way to a given point. And for this reason, this here is immediately much more complicated than in the one-dimensional case. And in order to see this, I would say let's use the next video to talk about examples. Hence, I really hope that I see you there and have a nice day. Bye.